Yes. All right. Boom. We are sailing forward with a flag that has a matrix on it, which is a little bit strange. And I am making things up. Okay, so here's we're on the wrong page. Here is a simple example of using the normal equation approach to do something pretty important, right? Which is fitting a straight line through a cloud of points. This is a big deal. People do this all the time. We have computers do it all the time for it. There are sneaky ways to do it that aren't as what we're going to do here, but the basic idea, this is an example taken from Strang's book, is we are going to have, if you like, an X and a Y type situation, and the error is all going to be in the vertical axis. So this is a case where we have, all right, so we're measuring some quantity, this B quantity, suspiciously B, 0, 8, 8, and 20, right? That's the values, and it takes on these values at some times, 0, 1, 3, and 4. So they're plotted here. And there's going to be some fit to this. We can roughly draw it at this point. That's not the exact fit or anything. And there'll be little errors here, right? So we can see that this is not going to work. It's pretty obvious, right? That we have 8 and 8 at different times. There's no way we can fit a straight line through this. We could fit a higher order polynomial, and linear algebra allows us to do that as well. The errors are usually called residuals, right? So there's a little error here. And we're going to fit it with a straight line. So, and we'll call our fit P, suspiciously, P of t. So it's some constant plus some other constant times time in this case, because that's the horizontal axis here. And we want this fit to be absolutely true. So at these times, we have the values of B, and we want them to fit this equation. So it's C at time, the equation at time 0 is C plus D times 0, and then C plus D times 1, C plus D times 3 at these times, 1, 2, 0, 1, 3, and 4. So we want that to be true. So we write down the equation as if it's true, and that's what this is, but then we put it in matrix format because we know that's the best way to do anything. So these characters equate, so there's really a 1 there, there's a 1 there, there's a 1 there, and there's a 1 there. So we can do this very nicely, right? So there's our a 1 vector, and there's a 0, 1, 3, 4, which just simply corresponds to time. So if we had a constant plus d times time plus e times time squared, there'd be another column here, and there'd be an e here, and it'd be 0, 1 squared, 3 squared, 4 squared. So the fit, this is an interesting thing, right? We're using linear algebra. The fit doesn't have to be linear. We could fit all sorts of funny shapes to things. That's a good thing to think about. Okay, so this is a column picture type setup, right? So C times this first column, D times the second column. We want that to equal these values of B. So now we have A, X, B. Boom, right? And as usual, we know this, we don't know these ones, and we know this. Okay, so it's pretty obvious that B is not in the column space of A, so we will set out to solve the normal equations, which we now understand to be totally awesome. So there it is, right? We're going to take A times X equals B, and then give up on it and solve this other equation, where we're looking for X star. And this is our X star, it's this CD. So let's, right, we take A transpose, put it in front of everything. That's what this is, A transpose. This is A transpose, and this is what we call B. Yeah. So let's do it. As I said, this will become, in the previous thing, that we end up with 2x2s for fitting straight lines. Right, so 4, this is the dot product of this first row with this column. The next one, so if you have a row of 1s, then this is basically saying just add up what you have in the column over here. So 1, 3, 4 is 8. We know this has to be 8 because it's going to be symmetric. But let's check it. 0, right, so it's 1, 1, 1, 1. We're summing this up, same thing. And then we have 0, 1, 9, 16. It's a bit hard, isn't it? So it looks like 26. Right, and that's times CD. So now it's a 2 by 2, and this equals, and so again, we have a thing we can figure out over here. So it's 16, that's a 36, and then 0 plus 8 plus 3 times 8, so it's 4 times 8, so it's 32, plus 4 times 20, 80, so it's 112 biscuits. So now we just solve this, right? Let's do it. Let's use row operations. So we like those things. Row 2 prime equals row 2 minus something times row 1. Yes, it does, and it's always, right, we're going to use 8 over 4. Boom. So, and I'm going to convert this to, well, it's all right. I'm going to convert it to the augmented version, right? So let's say this is, I guess I'll do the right thing. A transpose A, augmented matrix, A transpose B. That's what these are. Whoop, it's the same as this. It's 4, 8, 36. Top does not change. The bottom one is changing. So we're subtracting 2 of the first row from the second row. We've done this a million times. So there's a 10 here. And then 112 minus 72 is at 40. Maybe. Okay, so we can solve this now. We just do back substitution, that's fine. Right, we're being pragmatic. We've got to our, this is U. Okay, so if we do that, then we get 10 times x, and we're solving, well, I've got them written down. I don't have to call them x star. So this is 10 times d equals 40. Let's get the equations out. 4c plus 8d equals 36, and then 10d equals 40. So we operate on this one first. This gives us that d equals 4, and then we can substitute into here, and it gives us c equals 1. 8 times 4 is 32, 36 minus 32 is 4, c equals 4c equals 4, c equals 1. Okay, so that's our solution. So we have c d equals, and we'll call it x star. I want to put it down the bottom, I don't know why. X star equals c d equals 1, 4. And let's be very correct. This is not an exact thing. It's our approximation. So that's our best fit. It does okay, right? So our best fit line equals P of t equals 1, the constant's 1, plus, okay, 4t. Right, we got it. That's pretty good. And you can compute the error for this, right? So the error, what we'd do is we'd say the error is equal to, as usual, b minus p. And we have to put in these estimates. So b is 0, 8, 8, 20. That's a useful thing to do. So what is p of t at the values 0, 1, 3, and 4? So you can see where it's off. There's a 1. At time 1, it is a 5. At time 3, it's a 13. And at time 4, it's 17. Right, so we get minus 1. It undercounts it there. 3, it's too many here. Minus 5 and 3. And then we can think about this. We'd say the error squared, right? So what's the magnitude of it? So it's 1 squared plus 3 squared plus 5 squared plus 3 squared, which is 44. So there's a 1 plus a 9 plus another 9, so it's 19 plus 24, 5, it's 44. That's a useful thing. So this is a gauge of how bad it is, right? simple exercise. Once we've got the normal equation set up, I mean, what I should say is, given everything we know, this is a simple thing to solve. It's just a 2 by 2. All this setup took a lot of understanding, but amazingly, we have something that works for some a really nice new way of understanding fitting a straight line. And as I said, it could be anything. I feel like I should add it, right? So if we had an E here, and this would be 0, 1, 9, 16. This is for P of t equals C plus dt plus ET squared. It's just sort of a side note, right? So that we would have another piece in here. And you could do anything. You could have, right, anything could work. I should say pt equals sine of something. You could do anything you wanted, as long as you turn into you've got some variables here, and we can set it up into an ax equals b problem. We know all about it. So that is, that's pretty cool, right? So this could be, I mean, if this was a fit of 1,000,000 points, right, we'd still end up with a 2 by 2. So let me note that. Always 2 by 2. So we could have here, 10 to the 6th data point line fit for 10 to the 6th. That's an example. Data points. Still 2 by 2 problem. That's kind of nice, right? So this is we're only trying to find two variables, but that would just go and sort of compress all of those numbers in a really nice way. Okay, next.